Let's start. Okay. Well, I'm back home. There's a whiteboard, there's me. Let's do it. Alright, introduction to RL. Okay, what is this? What is reinforcement learning? Reinforcement learning is a subset of artificial intelligence that focuses on the idea of exploration. Whoa! What does that mean? So if this is AI, RL is like a subset of that. And like I said, specifically focused on exploration. So let me talk to you about what that means. In traditional supervised learning, let me grab a different marker. This one's kind of dying right now. You have labeled data, right? You have data that you have like an input and an output. So if I have a picture of a dog, then I also have the label of the dog, right? If I have a positive sentiment for a piece of text, then I know it's positive. I know how good it is on a scale of 1 to 10 or something like that. Like we're doing classification here. So there's an input and there's an output, or we're doing regression, right? So for every x, there's always an associated y, right? And then I collect a bunch of these, call that my data set D, and then my goal, right, is to create a function that given an unseen x, some x that we haven't seen before, to give me what it predicts the y should be, right? This is supervised learning, okay? So our goal in supervised learning is to learn this function. Okay. So in reinforcement learning, it's a little different. It's interesting because we're not given any of these y's. We don't know what this is. Okay. So we're like, okay. So you're like, okay, if you're not given the output, then how are you supposed to figure out what to do, right? Anything goes now. What do you mean? What is good? What is bad, right? That is a great question. So if you have just a bunch of x's, then what are you going to do with that? Well, actually, you can do all sorts of interesting things. That's called unsupervised learning. So reinforcement learning is still a little different from that. In reinforcement learning, it's more about exploring. All right, it's more about like exploration. So here's what I mean by that. It's instead of just having like this x to y mapping that we're trying to learn, we instead have this whole world, right? We have this whole world to explore, and we're gonna call this world the environment. Okay, so we have something called the environment, and the environment is made up of states and actions. So what I mean by this is that the states make up the environment, and how you transition between different states, that's what an action is considered, or the dynamics of the environment, right? So if I'm allowed to turn left at the stoplight, then the dynamics of the environment, that's what allows me to do that. Yeah. Okay, so now I'm turning left. And so the action there was turning left, and now the new state I'm in is like I'm more to the left than I was before, right? So that's states and actions. This is the environment. And to make this a little less abstract, because it's going to be a bit of a ramble, because I'm kind of just ad-libbing this, but hopefully it's still going to be useful. And I know you can't really tell me if I'm going too fast because you're just watching this, but yeah, hopefully you can keep up. Sorry. Yeah. So to make this more concrete, like let's think about some of the problems that reinforcement learning is trying to solve, and then you can kind of see like why we're formulating it like this, like what the motivation is, what the point is, right? So some problems that we can try to solve in reinforcement learning are like chess, right? Go. Big video games, MMORPGs like League of Legends, right? And what I mean by solve is like creating the best players, like better than the world's best. Dota, right? And there's actually examples of reinforcement learning algorithms beating I don't know about league, but in the other three, like beating the world's best at all of these things. Um, yeah, so there's all sorts of crazy things that you can do with reinforcement learning, and of course, right, the reason I'm interested in this is because right now for me, this looks like one of the most promising directions to pursue general artificial intelligence, and so that's why I'm attracted to this. Obviously, in real life, we're not given this why. We need to figure that out for ourselves. So that's what kind of naturally drew me to reinforcement learning, and it's been really, really interesting so far. So that's why I kind of just wanted to share some of the stuff that I've learned along the way with you guys today. Okay, right, so this is like some of the stuff you can do with reinforcement learning, or like play video games, right, like Atari Breakout is a great example. And today, you know, we're trying to apply this to robots. So robotics is a huge field of research. Like, how do I get this robot to walk forward without telling it anything in between, okay? All I tell it is like, okay, I want you to walk. It doesn't understand anything about mechanics, about physics, about its limbs, okay? All it's given are its actions, right? And some observations, some states, and it's supposed to figure out everything else. And okay, so what do I mean by everything else? Let's mathematically define that now. Okay, so we have states and actions, right? And what we're going to do is we're going to introduce another thing. This is the final piece of the puzzle, is the reward. Super important. This is probably the closest analog you can think of for the output. Okay, so like if this is supervised learning, you can think of X kind of like the state, okay? And then the reward is kind of like the Y. So sort of, not really. It's not a perfect analogy, but this is kind of like the idea. Okay. Also, actually, no, that's not very good. Just scratch that. Yeah, that doesn't make sense. But okay, so let's say that this is the states that we have, right? I'm going to define these transitions. Right, so this might be like state 1, this would be state 2, state 3, state 4. And then, you know, so in state 1 I can take 3 actions. I can take action 1, action 2, action 3, action 4, so on and so forth. And maybe with each action I get an associated reward, right? So like maybe here I get like, and the reward is a function for each state and action. So maybe the reward is like, here it's like +2, right? Maybe here it's like +0. Maybe here it's like -5, right? And then maybe here it's like -10. So in this case, the algorithm would try to go to state 4 because this is where it gets the most reward, right? So every time it would try to go to S4, it would try to learn how to get to S4. So starting off, it has no idea anything except for what actions it can take. It doesn't know what states are available, it doesn't know the rewards. And so the idea is that over time, you know, it's going to try to learn this environment, right? It's going to try to learn how to interact with this environment and maximize the total amount of reward. So this is what's going on at a high level. I'm going to dive a bit into the math now, so I'm gonna formalize this. If you can't quite keep up with this bit, don't worry. It's not too important. Okay, it's important if you want to do like work in this field, right? Like it's important from a mathematical standpoint, but like from an understanding perspective and like from what you can get out of this lecture, you don't feel like you have to keep up with this at all. So just skip ahead if none of this makes sense to you. Okay, but I'm going to formalize this now. So this is actually what's considered a Markov decision process, an MDP. The MDP refers to this tuple of mathematical objects. We have the states, like I mentioned before, the actions, the reward function, and actually, yeah, that's like the main 3. I can completely define all 3 of these with a probability function, and this is why this is going to get a little crazy. I'm going to define a probability of transitioning to the next state and getting some reward R given the action that I take in the current state. So what this means is that both the reward the reward has a distribution. It's stochastic, right? It's random. So if I went from S1 to S4, maybe one time I get +2, maybe the next time I get -5, maybe another time I get 10. So the reward is not fixed, it's actually random. And then the other thing is that the state that you transition to is also random. Okay, so this is also a stochastic thing. So if I take action 3 in state 1, I'm not guaranteed to go to S4. In this like simple example, I am, because I've only drawn it here. But in the full MDP, I can go from S1 to any range of states, right? Like if I take a state, if I take an action A3 in S1, maybe I go to S6, maybe I go to S7, maybe I go to S8, right? So that also has a distribution. Okay, so the state is, so the state is some Rn. So you could consider this like the observation of the state. So an example is like, let's say that I wanted to teach that robot how to walk, right? Then maybe the states are the position it's at, the velocity that it's moving at, okay? Like the current angles that all of its joints are at, the amount of like battery it has left, like right, the amount of power it has left, the current acceleration, right? Like that. Maybe those are like the states. So that's Rn, and then our action is going to be Rm. So maybe we output like, okay, so joint 1 should have this much torque, joint 2 should have this much torque, joint 3 should have this much torque. So M and N are separate, and then our reward function R is going to be a real number. So we're going to go from S and A to some R. Okay. So you can imagine with like this function, you can find like the probability of getting a reward in AS is equal to the integral of S prime R given AS ds prime. This is just summing up or integrating the joint to some marginal. And so on, right? So we could write the same thing for the probability of transition to some state. And so this would be all the possible actions within that, or this would be over the real number line. And then this one would be over all the possible states that you could take. So negative infinity to infinity. Okay, that's good. So the reason I drew these three was like, imagine if I started in some state here, okay? And maybe this is like when I wake up, right? So my goal, right, is to try to hit this happiness one like 95% of the time. But you know, that doesn't usually end up happening. Maybe I end up here most of the time. Let's make sure this is actually recording. Okay. Okay, good. Yeah, so like, so, you know, someone who's depressed, maybe it's like 90%, right? And then this is like 9% and this like 1%, right? Not great. Maybe this reward's like -10, maybe this reward's like 0, maybe this reward's like 100, right? And then someone who's like super happy all the time, maybe it's like 99%, right? So that's what I mean by like the distribution isn't fixed. And here, right, this is actually discrete. So the amount of the amount of states you can transition to are just 3. But you can imagine that there's actually like a gradient, right? Or there's like some sort of interpolation. Maybe you can be sort of happy or sort of not happy, right? Or maybe there's like a whole range. So the idea is that, you know, we can make this as complicated as we want, no problem. But you know, as long as we can figure out how to explore effectively in this framework, then we'll be able to solve any range of these problems. And that's the power of reinforcement learning. It's so generalizable. Like, it can solve all sorts of different problems. Okay, so now let's define the objective. That's the next step. Sorry, give me 1 second. And the reason I'm making this video is because I want to make another video on uncertainty estimation, which is the topic that I'm currently studying in RL, and that will be coming soon. I'm not sure when, but it'll be coming soon. Alright, okay, let's see. So, yeah, RL objective. Alright, our states, actions, and rewards over here. We have our probability of S prime R given AS over here. Okay, RL objective. So, okay, final thing I have to introduce. I'm going to introduce something called an episode. So our Markov decision process earlier was just something like you start in a state, you take an action, you get a reward. Then that gives you a new state, you take a new action, then you get another reward, so on and so forth, right? Until I reach some final termination state that like says stop. Okay, I'm done. This is called an episode or a trajectory. Okay, so I'm going to denote this with tau. So tau is my trajectory. So far so good, right? It's just like here to here. So this looks like this is called rollouts, right? Like I'm rolling out my poly. Okay, I didn't get to that part yet. That's a sneak peek. I'm like going for it. I'm trying out my agent. I'm trying out this guy, seeing what happens. And just another good graphic for you. Right, so the agent is what we're trying to train. The environment is what it interacts with. The environment gives the agent a state and a reward. And then the agent will give it an action. So this is the basic reinforcement learning framework, okay? Okay, cool. So now that we've defined these things, we can play with this a little bit. The goal of RL, okay, is to maximize the following function, J, where J, there's many different ways to formulate this, but I'm going to do the one that I'm most familiar with, is the sum of the discounted rewards. Okay, so what's happening here? It looks like, okay, it's actually not that bad. This is just a discount, okay, which means that I'm going to value the things in the future less. So as I go further in the future, this reward is going to matter less and less to me. When gamma is equal to 0, that means that future things matter as much to me as things in the current. So like I'm thinking all the way into the future, okay? When gamma equals 0, okay, sorry. Yeah, so zero is completely greedy. My bad. So when gamma is equal to 0, you're actually just fixed where you currently are, and you're not looking at all into the future. You say, all I care about is what happens to me next. I don't care at all about what happens. I don't care at all what happens right after what happens now. Okay. And then gamma equals 1 is the opposite. Gamma equals 1 is I'm going to think all the way into the future. So the sum of all the rewards here. So if I got like 5, 6, 7, right, and my gamma was equal to 0.9, then my sum here would be 0.9 times 5 plus 0.81 times 6 plus 0.729 times 7, right? So that would be my objective, and that would be like what this thing is, and I'm gonna call this the undiscounted reward. And I'm actually not quite done yet. Also known as the return, or sorry, discounted reward. This is considered the discount. Not quite done yet. I actually still have to do an expectation. And my expectation should be over the trajectory. Okay, and I'm going to find one last thing, which is the policy. So the policy should give me some sort of action given a state, or some distribution of action, the probability that I should take an action in the state. So this would be like a non-deterministic policy, and then this would be a deterministic policy. So this should give me a probability distribution. So the idea is like, okay, in this state, what should I do? And then this one is like the probability that I take any given amount of actions in the current state. Okay, so that's my P. That's my pi. That's my pi policy. So the objective is to maximize the expected value of my discounted reward. So my goal is to max with respect to pi j. Right, this is my goal. This is my goal. This is what I want to do. And yeah, there's all sorts of interesting ways to do it. Kind of like the two main approaches. There's model free, there's model based. Not going to go into that right now, but yeah, this is kind of the introduction to reinforcement learning. The next thing that you would want to learn if you want to continue is learning about Q functions and value functions, which are kind of just the same thing. And like one is just, they're kind of, yeah, you can always get to one from the other. And then from here you would want to go to DQN. And then from DQN, probably like A2C, MTD3, DDPG, and then SAC. So this is just like the state-of-the-art algorithms, the order that I'd recommend learning other stuff is. And I'll paste a bunch of useful links for learning more in the description below. Okay, hopefully that was useful. Hope you enjoyed that. Thank you very much for watching. Thank you very much for your time.